Alright, this is going to be a video on section 4.4 that's going to be tangent planes and normal lines. So recall a line through the point x naught, y naught, z naught with a direction vector of u, which is equal to the vector abc. X equals x naught plus a times t, comma, y equals y naught plus bt, comma, z equals z naught plus ct, and symmetric equations x minus x naught over a is equal to y minus y naught over b, which is equal to z minus z naught over c, provided a, b, and c. Those are two different ways of writing the line. Also, we can write it as like kind of like an ordered triplet for graphing. So it'd be parentheses x naught plus a at, comma, y naught plus bt, comma, z naught plus ct, and then close your parentheses. Recall a plane through the point x naught, y naught, z naught with normal vector n, which is equal to the vector abc. Your plane would be a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and that's going to be equal to 0. For functions of the form z equals f of xy, we'll rewrite it as f of xyz is equal to f of xy minus c, and that'll be equal to 0. So we have an image here from the OpenStax Calculus Volume 3. I believe it's on page 393. And it says, let S be a surface, f of xyz is equal to 0. Let r of t equal x of ti, y of tj, plus z of tk be a curve through p naught. And so we have two curves, one there, and then we have the tangents to the curve here and here. Okay. All right. So what we can do is, because this is a curve on the surface, it satisfies f of xyz is equal to 0. So f of x of t, comma, y of t, z of t is going to be equal to 0, and then for all t. If f is differentiable and x prime of t, y prime of t, and z prime of t exist, then from the chain rule, we know that the derivative of f of t is equal to 0 because f of xyz is equal to 0. And also, by the chain rule, if we take the derivative of f prime of t, it's going to be partial derivative with respect to x prime of t, plus partial with respect to y of f, y prime of t, plus partial of f with respect to z prime of t. And that's going to be equal to 0. At the point x naught, y naught, z naught, this becomes the gradient of f evaluated at x naught, y naught, z naught, dot product with r prime of t. And so this is going to be equal to 0. And so if two vectors dot product, so if I take two vectors and their dot product is 0, that means they're orthogonal. So the gradient is orthogonal to the tangent vector of every curve through the point p naught. So again, r prime of t is going to be a tangent vector to a curve on the surface. So all tangent lines lie in a plane normal to the gradient of f evaluated at x naught, y naught, z naught, and contains the point p. And so you have your tangent line here contained in the plane and the tangent line here contained in the plane to those two curves on the surface. Okay. All right, so let's go ahead and do a little bit more definitions, and we'll jump into an example or two. Okay, so tangent plane and normal line. Let f be a differentiable function at the point p is x naught, y naught, z naught on the surface S given by f of x, y, z is equal to 0, such that the gradient of f at x naught, y naught, z naught is not the 0 vector. 1. The plane through p that is normal to the gradient of f of x of the gradient of f of x naught, y naught, z naught is called the tangent plane to the surface S at point P. And then the second thing is the line through P having the direction vector as the gradient of f evaluated at x naught, y naught, z naught is called the normal line to S at P. So the equation of a tangent plane, in other words, would be the partial derivative And so this would be the tangent plane at a point x naught, y naught, z naught on the surface. Be the partial derivative of f with respect to x evaluated at x naught, y naught, z naught times the quantity x minus x naught plus the partial derivative of f with respect to y evaluated at x naught, y naught, z naught times the quantity y minus y naught plus the partial of f with respect to z, partial derivative of f with respect to z of x naught, y naught, z naught, and then times the quantity z minus z naught, and that's going to be equal to 0. So you get your normal vector from the gradient evaluated at the point. So let's do an example here. Example number 1, find the equation of the tangent plane and the equation of the normal line to x squared plus 2z squared equals y squared at the point 1, 3, and negative 2. All right. So x squared plus 2z squared and minus y squared is equal to 0. So we'll subtract y squared from both sides of the equation. So that means our function f of x, y, z is equal to x squared plus 2z squared minus y squared, and that's going to be equal to 0. So I guess we can sneak that in, equals to 0. So the gradient of f of x, y, z is going to be 2xi minus 2yj plus 4zk. Now we're going to evaluate the gradient at 1, 3, and minus 2, which is going to give us 2i minus 6j minus 8k. And this is going to be your normal vector, so that's going to be the direction vector for your normal line, and that's going to be the normal vector for your plane. So if we do our tangent plane, it's going to be 2 times x minus 1 minus 6 y minus 3 minus 8 z plus 2, and that's going to be equal to 0. Okay, and then our normal line, so our normal line is going to be 1 plus 2t, 3 minus 6t, and negative 2 minus 8t there. So you see your normal vector, 2 minus 6 and 8, 2 minus 6 and 8 in your plane, 2 minus 6 and minus 8 in your normal line. And then we had the point 1, 3, and negative 2. So you can see that in each there. Okay. So not too terribly difficult to find the normal line and the tangent plane. Now I'm going to hop over to the graph here. And so x squared plus 2z squared equals y squared. If you set that equal to 0, we have, it looks like some sort of elliptic cone along the y-axis. And then I have the points. What point did we do? 1, 3, and negative 2 down here. Okay, and then you see your normal line. So there's your normal line. And then we also have the tangent plane there. I think I took another picture of this using GeoGebra 3D. It's a free software, so you can try it out yourself, and it'll allow you to rotate it around. So here's another perspective of it. See a little bit more of it. So you can see that tangent plane right here, and then you see the point, and then also the normal line. Okay. All right. Let's go back, and we're going to work out one more example. Okay. Okay, so our example number 2, we're going to find finding the equation of a tangent line to a curve. Find the tangent line to the curve of the intersection between the two surfaces. So the surfaces are going to be f of xy is equal to x squared plus y squared minus c is equal to 0. And g of xyz is equal to 4 minus y minus c, and that's going to be equal to 0. They're going to give us the point 2, negative 1, and 5. And then we're also going to find the angle between the gradient vectors. So for part A, we want a tangent line. So the tangent line needs to be orthogonal to both the gradient vectors. Okay, so we want it to be orthogonal to both those gradient vectors at the point 2, -1, and 5. And so then I would put it in a tangent plane also. So let's go ahead and find the gradient of f, which is going to be 2xi plus 2ij minus k, and the gradient of g. So there's not going to be an I component, so it'll just be negative j minus k. So the gradient of f, evaluated at 2, -1, and 5, is going to be 4i minus 2j minus k. And the gradient of g, evaluated at 2, -1, and 5, is just going to be negative j minus k. Okay, so if we want this tangent line to be orthogonal to both those gradient vectors, what we can do is we need the tangent, we need the direction vector. So what we're going to do is we're going to take the cross product of these two vectors, and that's going to produce a vector that's orthogonal to both of them, and that'll give us our direction vector for our tangent line. So we're going to go ahead and do our cross product, set up our little matrix to just kind of help ourselves out. Okay, and so we'd cover up the I column, and then we'd have -2 times -1, which is 2, minus -1 times -1, so that essentially becomes 2 times 2 minus 1. Okay, all right, and then we'll do the j. So then you're going to have 4 times -1, which is -4, and then minus 0 times -1, so 4 minus 0 is, sorry, it's -4 minus 0, which is going to be -4, and then remember the j component is the opposite sign. Okay. And then finally we'll do the k component, which is going to end up being -4, so we'll cover up the k column, and we'll have 4 times -1, which is -4, and then minus 0 times -2, which is going to be 0. Okay, so just -4 there. All right. All right, so that's going to be our direction vector to our tangent line. And specifically our tangent line to the point 2, -1, and 5. Okay. So our tangent line, so the point 2, and then our direction vector is 1, so 1t. Okay, for the x or the I component. Next point, next is the y. We want to go through -1, and the direction vector is 4t. And then finally 5, and then the direction vector would be -4, and then we'll put the t on that. So that gives us our tangent line. Okay. Part B, we want to find the angle between the gradient vectors. So it's kind of like finding the gradient between two planes. You find the gradient, finding the angle between two planes, you find the angle and absolute value of the gradient vectors. So that's what we're going to do there. We're going to find the acute angle, so we're going to take the absolute value. So that's going to tell us that theta is equal to the cosine inverse, okay? And so we're going to dot product 4, -2, -1 with 0, -1, -1 in absolute value, and then divided by the magnitude. So 4 squared plus -2 squared plus -1 squared under the square root, that whole thing, that's the magnitude of the gradient of f at 2, -1, and 5. Gradient of g at 2, -1, 5 would be 0 squared plus -1 squared, and then plus another -1 squared. Okay, So that gives us theta is equal to the cosine inverse of 3 divided by the square root of 21 times the square root of 2. And that's going to be approximately 62.42 degrees. So that'd be the angle between those two gradient vectors. Okay, and I went ahead and put this into GeoGebra on the last slide here so we can take a look at it. Okay, so you have your z equals x squared plus y squared, so it's going to be your elliptic paraboloid. Z equals 4 minus y, that's your plane. And then where they intersect is this point A. Okay, all right. And then we have your tangent. Okay, so that's going to be the tangent there. And then we have our two vectors here and here. And we found the angle between those vectors to be 62.42, yeah. And here's one more picture here. I decided to do one more so that you can kind of see the tangent line a little bit better. So here's your tangent line to the point of intersection there. Okay. All right. So this was a little bit of a shorter video. It's a short section. It's not too long. So we'll see you next time, and then in the rest of chapter 4.